Hello, Roman. Welcome back to a series of videos of building the convolutional neural networks from the scratch. This video will be the continuation of the previous one, where I decided to find a different material to plan what I'm going to do and kind of take a step back and reread, or in this case, re-listen or restudied the information about the convolution that I studied before with my attempts that I tried to implement this and understand how I can structure the data in order to properly integrate it into the code base that I wrote in the neural networks from scratch series. And I'm using right now this video that's called Convolutional Neural Networks from Scratch, Mathematics and Python Code. So far, it is the best example. I mean, so far, this is the best material I can use, or I found, to understand how it should be implemented like really from the scratch. So it uses NumPy as the library to work with the data. All of the things I actually built using the NumPy, including the dense layers and so on and so on. So yeah, in the previous video, I took a step back and took a look at the forward method. And I'm making some notes and actually decided to go with the proper implementation, like in the video, with defining the number of the input channels, like input shape and where it is, for example. So for the kernels, I would be able to specify the depth, meaning the depth of the convolutional layer, and input depth, meaning for example, for the RGB image, number of the images or number of the channels that we'll use, and then we'll use the kernel set. Most likely, I will abandon most of the code that I wrote before and kind of start from the scratch. It might look like I kind of lost some time, but actually it's not like this. The main thing that I tried to attempt and implement it, and now all of the things actually makes more sense to me. So in this video, I will just go over the backward path because that's kind of, I had actually more questions to the backward path than to the forward path. So let's see.
Okay, now comes the hard part. In order to update the kernels and biases, we need to compute their gradients. If you remember from the last video, this is how we proceed. We are given the derivative of E, the error of the neural network, and we need to compute
But the author referenced the previous video. I think this is the video regarding the dense layer implementation. I'm not going to dive into the foundation of this part, like what is derivative and so on and so on, because it was covered a lot during the neural networks from the scratch series, as I've been following the book where we dove through, where I did the deep dive into this part.
two things. On one hand, the derivative of E with respect to the trainable parameters of the layer, namely, the kernels and biases. On the other hand, we need to compute the derivative of E with respect to the input of the layer, so that the previous layer can take it as the derivative of E with respect to its own output and perform the same operations.
So yeah, so we will use this one, the derivative from E with respect to the input as the input value for the next layer, which is, well, in the backward path, kind of the previous layer. And this one we'll use to actually adjust parameters for the training purposes.
So we will start with the derivative of E with respect to K. This is the equation of the forward propagation. If we expand the sum, we get this. Now, Dealing with all these terms can be quite daunting. Therefore, I'd like to crop that equation just for a moment and work out the calculations on a simplified version. Y equals b plus x correlated with k. If we actually write down what each output variable is equal to, one piece out of 3. The next is equal to x1 correlated with the derivative of e with respect to y2. And of course, there is nothing special about k21. This can be general.
I'm not going to watch this, dive into the math right now, as it's, well, if you want, you can watch them too. And the second one, I already watched it before, so I'm going to focus more on the code part.
I will fast forward a bit. This is the actual equation, but let's work on a simplified version.
Okay, so this is for the biases.
Derivative of e layer. This one is quite surprising, you'll see. Here we go again. We have the forward propagation equation. We will work on a simplified version, but for every x, j. And since we're good people here, we will compact this inside a sum.
Yeah, so there is a main difference that we will use the full cross correlation for the derivative for with respect to the inputs.
Don't hesitate to take a moment to verify this is all clear to you. After all, if we're doing this from scratch, it is to understand every step of the process. So, we finally have the 3 equations that we needed to complete the backward propagation of the convolutional layer. Let us code the backward method.
Okay, so this is the part that I'm mostly interested right now.
First, we start by initializing empty arrays for the kernel gradient and the input gradient.
Okay, so for the backward, the kernel gradient uses the same shape as the kernel, which means that it's a 4-dimensional array with the depth of the convolutional layer, with the number of the input depth, meaning the number of the channels, and the kernel size. And then we have the input gradients, which is the same as the input shape, meaning that it reflects the structure of the input image. For example, if it's an RGB image, that I will have the 3-dimensional array. If it's a grayscale image, for example, for the fashionista datasets, it means that we'll have 2-dimensional array.
Next, we compute the derivative of e with respect to kij inside 2 nested for loops that go through the indices I and j.
Okay, so we're going through the depth of the convolution, then we go through depth of the input data, and we compute the kernel gradient I and j as the cross correlation, as the fairly cross correlation between the input slice of the j. So this is going to be a 2-dimensional array representing one channel, and the output gradient. So the output gradient is actually the thing that we're taking from the previous one, right? So this is in my case, that's going to be the input, and the input is going to be in the shape of the output, so in this shape. This is why we're using the I to index it, because here we will take the gradient from the next layer, which most likely will be the max Boolean layer, and this is going to be the... Okay, so this is the cross correlation, valid one, between... So for example, okay, so if we have only one kernel, for example, we have one kernel and we have only one channel this is going to be just one cross correlation. If we have RGB image with the two kernels, then we'll have this 3 times and 2 times. That was 6. Okay.
See how we literally translated the mathematical formula into code. Next, we compute the input gradient.
And then we have the input gradient. This is what I have as the inputs, right? So this is the inputs, and this is the weights corresponding to what I had in the tensor layer, right? And yeah, so we return the input gradient. In my case, I will just store it. And so for the biases, we'll just take what we took, and meaning that the biases will have the same, shape as the output shape. This is why we can do something like this. So we just use the learning rate, and we took all of the data from the D input that we had. For the kernels, as we compute the kernel gradient. Okay.
Although this might seem weird to put this line here, if you think about it, it's exactly the same thing as computing this inside 2 separate for loops. Notice how this time we used the convolve method and specified the mode to be full instead of valid.
So we're taking the two-dimensional stuff from the D input that we had from the next previous layer, and then we're taking the kernel values, and then we do full cross correlation. So it will output a bigger shape.
About the bias gradient, we don't have to calculate it since it is equal to the output gradient, which is given as a parameter to the backward method. So finally, the last step is to update the kernels and biases using gradient descent and return the input gradient. Look at that.
Okay, so for the backward method, okay, so let's make some notes. Okay, so this is actually the inputs in my case, right? Oh, the values. Cool. Not the inputs. It's the input, it's something that we pass into the backward method, and that became the values. Basically, yeah, it's the values slash deans, right? So this is for this one. For the learning rate, I will guess I will need to inject it into CNN layer somehow, because currently the current learning rate is held by some optimizer. Because if we take a look at the optimizer, we actually have the optimizer interface, and we have this get current learning rate, and well, this is actually used by the optimizer. For example, we have the update params, and the implementation, for example, in Atom, for example, where we have this current learning rate. So probably I will need to inject it or have access to the optimizer somehow. So inject it or have access to optimizer. That I will need to think, but for now let's do it like this. Okay, so the kernel, what is the kernel gradients? The kernel gradients, kernel. Okay, so the kernel gradients, we use it to update all kernels, and they have the shape of the shape is the shape of kernels itself, right? Meaning this is the four-dimensional array, right? We have the kernel shape. Where is this one? So we have the kernel shape here. So this is the four-dimensional one. Okay, then we have the input gradients. And the input gradients, this is what we output as the inputs, right? And same shape as inputs. Well, this is how it's going to become interesting, because for this one I need to actually take into account number of input samples for forward/back passes, right? Because here the result input gradients, because the result, the inputs, this is the trickiest part for me, because in this one it does it one by one, right? And it computes the, for example, if we take a look at the input gradients, it just returns it, and this is going to be used by the next layer. We'll get back to this, but for example, for the kernel gradients, it means that this gradient for the weights update. This corresponds to one input, right? But for example, in the dense layers we had, I had, for example, the forward path and I had the backward path, and I had a bunch of the gradients corresponding to several of the inputs. So the thing is that I don't understand is what to do here, like how to actually change. What I don't really understand is this. How to actually change the weights given the fact that the t-values will have multiple samples at once. Should I average them? Should I go actually just one by one and do this change? I mean, if I would go, for example, if I would change the implementation of the train model and just go one by one, so I will pass only one sample for the forward path and the backward path, then that's what will happen for the convolution. We'll just go one sample after another and just adjust values one by one. So maybe that's just use for loop or samples. This is the question I'm not sure how to answer right now. Okay, so this one is actually, again, this is the self dots. Well, okay, this is basically a layer the inputs, all right? Okay, and for this one, the trickiest part will be to get the access, because like one of the problems that I have in general that I need to store 4D or 3D array as 1D array and somehow process it. Because for example here, yes, you can store it as a four-dimensional array, but since I'm using the Golang, where, like this, where I have the example. So where, for example, one row will have to store all of the things, at least for the data that I'm exposing outside for compatibility. Or I'm doing another way. So this is, how it should look like. Or what I'm considering to change, I'm not sure yet. Wait. Is to change this to like layer interface, because in that case I can do some downcasting and get access to the, not just because the problem that I faced before is just not that convenient to work with. For example, you have a one-dimensional array that represents actually four-dimensional data, and you have to implement all of this index math to properly access the data. For example, imagine that this is not, well, even that it's a three-dimensional array. For example, I need to have a slice of this. No, I need to have slice of this, and then add this and something like this. So I can create a, for example, I can get access to the specific part of the two-dimensional part. For example, when I will need to compute the cross correlation for the this one. When I will need to compute the cross correlation, for example, for this part, and imagine that this is the one-dimensional array. I will need to take I and take J, and then I will be able. Well, I mean, it's not hard. It's just not that convenient to oppose like having a really four-dimensional array where I can do stuff, like, I don't know, layers, or, kernels, like I, J, and that will return me to the array. This is much easier to work with than, I don't know, having something like kernels and I multiplied by, I don't know, what it will be. Kernel size multiplied by the kernel size multiplied by the input depth, and then we will need to, and it will be one-dimensional array, and then I need to reshape it into 2D. I mean, this is doable, I mean, for sure, but not that convenient. Okay. But this is what most likely I won't have to do. Okay.
What number is written on a given image? The classification at the end of a network, we use them. Let's start with the reshape layer. The reshape layer, like all the other layers, inherits.
This is something I would not need actually, as long as I follow this convention of having the output as two-dimensional array where one dimension corresponds to the samples and the second one corresponds to all of the data. In that case, I don't have to do this. This is actually kind of a proxy from convolution and the max pooling. By the way, where is the max pooling? Oh, they actually don't have the max pooling. Maybe actually I can emit the max pooling for now. Right? Convolution, sigmoid, reshape. Maybe I can do something like this. The reshape, you can see that it's 5 by 26 by 26. Interesting, why 26 by 20? Oh, 5 because the depth of the convolution, 26 because of the reduced size of the convolution itself. And then we reshape it into something like this. So we have one-dimensional array that we can connect with dense layer. So this is, we will have the number of the inputs, and then we'll have the number of the outputs, and that's it. And then we'll have the sigmoid. But the interesting part that this example actually doesn't have any max boolean, so maybe I should omit it too, and do not try to implement it at first, which is actually an interesting idea. And I will just focus on the convolution itself. I mean, probably I will do this. Okay, so we actually took a look at this one. I will focus on the convolution only. I think this is the better approach to do, but I will focus on the ability to, to be it more configurable as it's here. Will actually make it easier for me the first implementation, because one of the problems that I had before is that I wasn't sure how to properly compute the derivatives for the max boolean, how to connect it with all of the things. So going step by step is actually much better. I think, and this is what I'm going to think about, but if we take a look, we have the convolution. Oh, we have the max boolean. I will leave it as it is right now. But for the convolution, I am going to actually remove all of the things and rethink how this is structured. So basically, I'm starting from the scratch. I mean, I'm starting mostly from the beginning, but sometimes you have to remove all the things you implemented and just start from the scratch. Probably second time it will be faster or better. I mean, I still have the implementation of the cross correlation, the valid one and the full one already, so there is no problem with this one. The only thing I need to think about is how I'm going to produce the output for the dense layer. And I will start from this one. So that's all for today. I finished with, recapping the information and made lots of the comments. I will still have some more things to check, but from the next video, I will again remove all the things and start from scratch. That's fine. But for now, thank you for watching, and I see you in the next video. Bye.